Hi guys, this is the fourth video of Dynamic Programming Algorithms video series, in which we focus on how to code dynamic programming algorithms in Python. In the previous two videos, I introduced the short spread problem and talked about how to solve it with Dijkstra's and Bell-Mulford algorithms. In this video, I will talk about Floyd-Warshall algorithm to solve this problem. To remind the short spread problem, let's recall the directed graph that we used in the previous video. Our aim was to find the short path from the source node, node 0 in this example, to each node. For that, we use Dijkstra's algorithm when all the edge weights are positive. And we use Bell-Mulford algorithm when some edges can be negative, but still there shouldn't be any negative weight cycle. Well, what if we want to find the shortest paths between all pairs of nodes? One simple method would be using Dijkstra's or Bell-Mulford algorithm for each node being the source node. However, we will need to solve n different problems with n being the number of nodes. Instead, we can use Floyd-Warshall algorithm. To illustrate how the algorithm works iteratively, let's consider three nodes. And let's suppose that we are trying to find the shortest path from node u to v. We define a set of intermediate nodes denoted by capital K, and letting capital K be an empty set at the beginning, we expand it at iteration such that capital K is a set of 1 to k at iteration k. While constructing the shortest path from node u to node v, we can use only nodes in capital K as the intermediate nodes along the path. More specifically, at iteration k, node k is added to the set capital K. Then, we check whether using node k in the path can improve the current path or not. To see that, we compare the length of the current path with the sum of the lengths of the path from node u to k and path from node k to v. If the length of the current path is smaller, we don't include node k as an intermediate node. Otherwise, we include node k and then update the path and its length. Notice that it is sufficient to look at this condition to decide whether to improve the path. Because if node k will be the part of the path, then the shortest path from node u to v should be a concatenation of shortest path from u to k and the shortest path from k to v. Now, let's introduce the notation before focusing on how we would write this pseudocode of this algorithm. WUV denotes the distance from node u to v. If there is no such an edge, then WUV equals to infinity. Also, WUU is 0 for each u. DUV denotes the length of the path from node u to v. Lastly, the number of nodes is denoted by n. In the algorithm, first we initialize the path length to the distance. Then, at each iteration k, we iterate for each ordered node pairs and check whether using node k in the path can improve the current path. For that, we use this condition. This is the part where we use dynamic programming, so the recursion. Before moving to how we can code this in Python, it's worth mentioning that the weights can be negative, but there shouldn't be any negative weight cycle. If there is one, the algorithm can detect it. Basically, after running the algorithm, if the shortest path length of a node to itself is negative, it means that there is a negative weight cycle. Now, let's code this algorithm in Python by writing a function called Floyd-Warshall. The inputs of this function are the nodes and edges, which I will show how we can write them for our example. The outputs will be the shortest path between all the pairs of nodes. Now, we initialize path lengths for each ordered node pairs and assign them to corresponding edge weights. But we call that the edge weights is 0 if nodes are the same, and the edge weight is infinity if there are no such edge. So that's why we initialize path lengths in this way. Then, as we iterate each node k, we have a for loop over node k. Also, we have for loops for each node u and v because we need to update the shortest path lengths for each ordered node pairs. Inside this loop, we update a path length if we can obtain a better path than the current one. The first part of the main function is the length of the current path from node u to v, and the second part is that of when we include node k as an intermediate node along the path. Lastly, before returning the shortest path length as an output, we check whether the graph has a negative weight cycle. Let's see what this function returns for our small problem. Before that, let's remove some of the edges. So here is how our graph looks like. Then we initialize nodes and edges as follows. Here how the output looks like. As you see, we can obtain the shortest path lengths between all pairs of nodes. So, in this video, I talk about Floyd-Warshall algorithm. I showed how we can find the shortest path between all pairs of nodes by using this algorithm. I hope that it was helpful. Please leave a comment if you have any question. In the next video of this dynamic programming video series, I will compare three algorithms that we use for the shortest path problem, Dijkstra's, Bell-Mulford and Floyd-Warshall algorithms. The comparison will be based on the space complexity, time complexity and capability.